Programmable logic controllers, discrete and analog signals. In this presentation, we're going to be looking at discrete signals, analog signals, broken conductors and analog signals, and finally we'll end with some equipment that has both AI and AO capabilities. Now, PLC input and output signals are divided into two categories. They're known as discrete signals and analog signals. Discrete signals are either 0 or 100% of the full signal strength. And when we say signal strength, what do we mean? Well, we think of them as zeros or ones of logic, and in the field, that would be like 0 volts or the full voltage of the control system. So maybe it's 24 volts, 48 volts, or 120 volts, something like that. Now there's a number of different devices that can offer us that type of input. For discrete input, DI, the presence or absence of voltage at the PLC card is controlled by the pilot device themselves. So things like limit switches, proximity sensors, the contacts of a relay, magnetic reed switches, and push buttons would all be examples of discrete input devices for a PLC discrete input card. Here's an example of a discrete input device. This is a temperature switch, which has a bimetallic snap disk inside it, which would then go convex if it is at 450 degrees or higher, and then make a closed connection. So, if the temperature is then raised in front of this device, the contact will close, and that will apply a signal of 1 back to the PLC terminal, which we can see here would be 24 volts. Now, discrete output devices are a little bit fewer in number. This is the presence or absence of voltage controlled by the PLC to energize a very small, low-power load. So the coil of a relay, small indicator lamps, and sometimes buzzers. Anything larger than this, the PLC would not be capable of controlling typically, and so we would run it through a series of relays or contactors. So in this situation, we can see the PLC is sending a signal out of 1, and that is what's energizing the indicator lamp, obviously through a PLC discrete output card. Now, what if more precise measurement or control is required? That's where analog signals come in. Analog signals can vary anywhere between 0 and 100% of the full signal strength. Although there are many different analog values in industry, they can be categorized into voltage or current. The two most common in industry are a 0 to 10 volt DC system or a 4 to 20 milliamp system. And yes, you're reading that right, 4 milliamps would be considered a 0% of the signal and 20 would be considered 100%, whereas on the voltage one, 0 volts would be equivalent to 0% and 10 volts would be equivalent to 100% of the signal strength. An example of an analog input device would be an RTD. When the probe is exposed to heat, the resistance of the device changes. When a voltage is then applied to the terminals of the device, the current flow will change due to Ohm's law. Now, analog input devices are devices that send a signal back to the PLC that is 0 to 100% of the maximum value. These are devices that are usually measuring quantities of distance, flow, temperature, pressure, light, or speed. Examples of these devices could be anything from flow meters to VFDs, adjustable dials, linear position sensors, another type of flow meter, strain gauges, and RTDs and thermistors. In this situation, an RTD has a positive temperature coefficient. As the applied temperature increases, the resistance goes down. When a voltage is applied, this has an inverse effect on the current due to Ohm's law. So right now it's at 20 milliamps with a rather low temperature. And if the temperature increases, the value of current goes down. And so you can see here it would be varying anywhere from 4 to 20 milliamps. The PLC could then determine what is the temperature that the probe is being exposed to. Analog signals are typically always present, only their magnitude varies. So this provides constant feedback to the PLC regarding the controlled process. So here are some examples of analog inputs. We can see here capacitive level sensor. This is probably some form of a temperature probe, RTD, and that's a flow meter. So we have all of these different devices that are analog inputs coming in. Now, analog output is something that receives a signal from a PLC that is 0 to 100% of max value. And these are usually devices that are controlling quantities of distance, flow, temperature, pressure, light, speed, or graphics even. So you can have anything from variable valve controls to variable damper controls to VFDs and maybe even an HMI screen that gives us real data that's being updated. So here's an example of an analog output. This is a variable damper with something called a BELIMO, and we'll take a look at this in a little bit more detail after. But depending on the signal that's applied to it, it will vary how much this damper is open, anywhere from 100% closed to 100% open. So if I increase the value of the output going to that actuator, it slowly increases and opens it wider. Analog signals are again typically always present, only their magnitude varies, and the PLC has constant control over the process. So here's an example of a PLC sending information to a VFD as an analog output. The VFD then controls the motor speed, and the motor then controls the dust collection system. The HMI is then connected to the PLC, and this is where we would set our values. So maybe I input the speed that I wish it to go, so there's both analog input and analog output that are going back and forth between the HMI and the PLC. After connection to the PLC, analog input and output devices must be set up in the PLC program. This setup process will require settings to be completed, such as the type of analog signal, minimums and maximums, and in the case of inputs, what the signal would be used for. The process of setting the min and max is often referred to as scaling. Now there's some interesting things that happen, and there are some advantages of using a 4 to 20 over a 0 to 10. And other cases, there's advantages to 0 to 10 over 4 to 20 milliamps. In this situation, I have a 4 to 20 milliamp analog input. 20 milliamps is low temp, 4 milliamps is high temp. And so we can see here as the baking chamber increases, we have a value of current that increases. Now, if I get a broken signal wire, what that can be programmed into the PLC as is an error. This type of signal should always be somewhere between 4 to 20 milliamps. If it's under 4 milliamps, it means there's a problem. And so the PLC could be programmed to recognize this problem and initiate actions to alert the facility that something is wrong. If we look at a 0 to 10 volt system, that won't necessarily happen because 0 to 10 volts, 0 means low, low flow. 10 means high flow. So right now we're at 90 liters per second, and there we're down to 10 liters per second, and we can see the voltage changes going back to the PLC analog input. Remember, the flow meter is measuring the flow of the water. It is not being controlled by the PLC. So if we go back up to 90 liters, we see 9 volts being brought back to the PLC, but what if there's a break in the signal wire? Well, 0 volts would then be present to the PLC. The PLC can only understand that 0 volts equals 0 liters per second of flow, and this could lead to problems because there's actually 90 liters per second flowing. So sometimes it'll make sense to use 0 to 10, and sometimes it'll make sense to use 4 to 20 milliamps. Sometimes the equipment you're using will dictate which of the two systems you need to use. There are different types of equipment out there that will utilize both analog input and analog output signals. A really common example is a VFD. This type of device will be capable of either sometimes voltage or current analog signals, and those voltage versus current signals will often be switched in the system with dip switches. So if we look in here, it shows that this PowerFlex 525 VFD is capable of 0 to 10 volt analog signals or 4 to 20 milliamp analog signals. It just depends on which one you happen to be using. And then we see here the 4 to 20 milliamp in analog signals here versus the 0 to 10 volt analog signals up there. Another example is louver actuators. So this is a Belimo, which is the brand name of most of the bright orange colored louver actuators. Louver actuators are slow-moving geared motors that will then turn a rod, which then moves or actuates louvers for air movement in an air system. They move slowly, and that's because you want the air system to not have significant fast changes of flow, because that can send shock waves through the system, but you also don't want it to be loud as all of the louvers open really quickly and loudly. In addition to that, by having it all move slowly, you reduce the wear and tear on the equipment. So on most of these systems, there will be analog input and analog output. The analog input comes from the PLC, and it tells it how far it wants it to open. The analog output sends a signal back to the PLC saying, okay, you want me to do this, but I'm closed right now, so now I'm going to start opening, and I'm going to show you how far I'm opening until I'm finally open to the value that you wish me to be. So this type of object will often have both analog input and analog output. And hopefully that gives you a little bit of a sense as to how discrete and analog systems function on a basic PLC system.